Welcome to How Natural Disasters Relate to Plate Tectonics. Remember, environmental science takes information and helps you to learn how these particular topics impact humans around the world, both in positive and negative ways. So, firstly, what we'd like to look at is the calculation of wavelength. Here's the formula. And remember, just like our density formula, this one can go into the triangle as well, so that you'll always be able to calculate for wavelength or velocity or frequency. Now, I like to remember that the wavelength one to me looks a little bit like a wave, and this is the Greek letter lambda. It's in its base form, the units are measured in meters. Velocity is the speed that the wave is moving in a given direction. So that's going to be meters per second, like meters per second up or meters per second down. Frequency, the wave crests that go through a point in a certain time, and it's done in cycles per second, which is also known as hertz. I'm going to stop sharing for a moment and we're going to take a look at a video that gives you some information about this, and then a second very small video that covers one really important topic. And that is that when a wave occurs, it's going to move through the medium. It's not actually going to carry the medium with it. And I promise after these videos that will make a bit more sense.
Ever seen a Mexican wave at a sporting event? The effect is a pretty cool display that goes all around the stadium, but no one has had to move seats. All waves can transfer energy from one place to another without transferring any matter. This is done by a series of disturbances or vibrations that carry the energy. Just like the people in their seats only moving up and down when it's their turn. Waves can transfer energy through solids, liquids, gases and empty spaces, otherwise known as vacuums. There are two types of waves, which we look at in more detail in another video, but the basic features are the same. These four words describe different properties of waves. Let's discover what each one means. The frequency of a wave is the number of complete waves passing a fixed point in a given amount of time. This time period is usually 1 second. This is what one complete wave looks like. So if this was our time period, the frequency would be 5. Frequency is given the symbol F and is measured in units called hertz. Hertz measure how many complete cycles per second. So how many people in our Mexican wave stand up every second. The frequency and period are often confused. The frequency refers to how often something happens, whereas the period refers to the time it takes to happen. The period of a wave is the time for one complete cycle, so the time taken for one person to stand up, wave, and sit down. This would be measured in seconds. When something happens repeatedly, we say that the event is periodic, and refer to the time for the event to repeat itself. The period of the Earth to orbit the Sun is 365 days. The period of a day is 24 hours. The period of a typical class at school is 45 minutes. Now for wavelength. The wavelength is the distance between a point on one wave and the same point on the next wave. For example, two peaks or two troughs. Wavelength is given the symbol lambda from the Greek letter and is usually measured in meters. Wavelength can vary hugely in size. X-rays are very short, visible light is here, and FM radio waves are much longer. So we've looked at the frequency, period and wavelength so far. Let's finish with amplitude. As waves travel, they create disturbance. The amplitude of a wave is the distance from the maximum disturbance to the undisturbed position. Think of a very flat sea, and then an incoming wave. The amplitude is the height of the top of the wave from the flat sea. Can you add the labels to these waves and work out the frequency? Notice that the top one is distance and the bottom one is time. Pause the video, work it out and click play.
Take a moment and see if you can work out what number 1, 2, and 3 are, and then see if you can solve for frequency. If you need more time, just hit pause.
Play when you're ready. Did you get them right? In another video, we'll be looking at wave speed equation.
Okay, now that video walks us through great vocabulary, walks us through the use of the formula. Now I just want to take one more look at a very specific feature that he discussed that I want to make sure you really grasp, because it's going to be so important when we start to talk about things like earthquakes. I want you to watch the ball as it rotates. I'm going to hit play. And as the ball rotates, look at how it doesn't really change position in space very much. It basically goes from the C to the N in a circle, like up here, just as like a reference. And you can see how it rotates around, but doesn't really go forward or backward in space. It moves generally perpendicular to the direction of the wave. In a moment, you're going to see, here it is. This is here to show you how when a wave comes through, it only disturbs a very small portion of the actual water column or the air column. All the particles that are deeper or farther away from that disturbance don't move really at all. And again, you can see how this rocks around in a circle and how the energy moves through, but it doesn't really move the diamond around anywhere. Again, we'll talk a little bit more about why that's so important when we start to talk about earthquakes. But since it's a property of waves, I wanted to make sure that you kind of saw, you sort of saw that now, and then we'll apply it when we get to earthquakes. I'm going to stop sharing and then go back to the PowerPoint to look at this again. Okay, this is just a picture that gives you the idea with a slinky about wave propagation and about how a wave moves through a medium. But I think it's a little bit more powerful on the next slide. This one here. What's occurring is this. Let me get a pointer. You have a ping pong ball that's dropped from a height. It's just about to strike the surface of the water here. When it does, it forms waves. You can see that there are two waves. As the waves move outwards towards the buoy, they're going to pass through the buoy. But look at the buoy's position in all of these pictures, here and here and here. Notice that the waves have fully passed through the buoy, but the buoy didn't go anywhere. And the same thing is going to happen with the yellow flagged buoy when they get completely past that. The waves pass through. They would raise the buoy up and lower the buoy down, but they don't actually push the buoy with the blue flag towards the one with the yellow flag. The distance there remains consistent because the wave passes through rather than moving the buoy. Sometimes this is confusing because we think about waves at the ocean shore, but the reason that the ocean shore waves behave the way that they do is for a different reason, and we'll cover that a bit when we get to tsunamis. Oops, I'm really sorry that I just closed out of my PowerPoint. Nicely done on my part. Sorry for this. Sorry about that. So here is the wave propagation again. Now, the last thing that we're going to look at is volcanoes. And when we look at volcanoes, what we see here is that magma is going to rise up through the lithosphere. It's going to reach a crack in Earth's surface. It's going to erupt and it's going to release lava, hot ash, and gases into the atmosphere. Here's a picture of how that's happening. Do you notice how, and let me put my little pointer on one more time. Notice how these islands form almost an arc like this or a C. That's because of plate movement. This is a long dead volcano, a medium volcano, and an actual island that is still under formation. You can see that it has the lower mantle, the upper mantle that's hooked to the crust, which forms a lithosphere, and the magma comes up through the lithosphere, comes out as lava, and is going to form these islands. We're going to watch a really cool video that hopefully will start to tie together for you how topics in environmental science all tie together and how what can seem like a really simple thing, oh, look, it's island formation, can really inform other portions of science. But before we do that, let's just cover a little bit about earthquakes and then we'll end on the video. All right, earthquakes. An earthquake is a breaking and shifting of rock at a fault. It creates seismic waves. Now, these waves are going to be able to travel, some of them through liquids, some of them through solids, and some of them through both liquids and solids. And that's going to end up being really interesting when we look at how earthquakes create destruction. The focus is the origin of an earthquake. The magnitude is the severity. It's going to be measured on the Richter scale. And then amplitude is going to be the size of these seismic waves. And of course, the larger the amplitude, the more significant the earthquake will be. There are several types of earthquakes. Technically, the scale runs from a 1 to a 10. We have never seen an earthquake larger than a 10 on Earth's surface in the modern era or since we started measuring. This is not necessarily to say that no earthquake could be over a 10. It just hasn't occurred, so we generally put it on this 1 to 10 scale. If a 1 earthquake happened, you wouldn't even be able to feel it. In fact, the general idea is that below a 1.4 or 1.5, the actual vibration or the actual size of the wave is so small that humans don't even feel it. Then we start to run on the scale from when it can start to cause a small amount of damage all the way up to creating catastrophic damage. Insignificant is below a 4. Minor is a 4 to 5. Damaging a 5 to 6, destructive a 6 to 7, major a 7 to 8, and anything larger than an 8 is great. Now, please keep in mind this little word over here at logarithmic. A logarithmic measurement means that a 4 to 5 is not 1 time greater, it's 10 times greater. So basically, a 4.0 to a 4.1 is 1 time greater. 4.1 to 4.2, 1 time greater. But a 4 to a 5 is 10 times greater because it's logarithmic. All right, tomorrow we're going to pick up with seismographs, but for now, we're going to finish out with a really cool video on island formation so that you can see how this stuff that we've been learning is actually being taken, used by scientists to inform information about Earth, but also being used to inform about other places.
Earth saw the birth of a new island, the first of its explosive type in 53 years. The blast was so large that nearby tourists caught the explosion on camera. Despite raging volcanic activity above and below the Earth's crust, an event like this is pretty rare, which is why it immediately caught the attention of Dr. Jim Garvin, chief scientist at NASA's Goddard Space Flight Center and Mars expert.
It should be a pile of basaltic andesitic rocks. That's what you expect in this kind of setting. But there's more.
What does a Mars expert see in the island that the rest of us don't? The new island, unofficially known as Hungatonga Hungahaipe, is located in the remote southwest Pacific, nestled between two other islands in the Kingdom of Tonga. It's the first island of its kind to erupt and persist in the modern satellite era, giving scientists an unprecedented view from space of its evolution.
There are other islands being formed, including ones near Japan. Very nice, lava eruptions, classic. But this one was special because there was this explosive element that reminded us, at first glance, not exactly, of the kind of eruption in Surtsey.
This is the eruption Jim is talking about. An island born from a similar explosive eruption in 1963 and one of only 3 volcanic islands that have survived in the past 150 years. Very early in Jim's career, Surtsey was the first newly formed oceanic island he ever studied.
Dr. Jim Garvin, Chief Scientist here at Goddard.
Years later, he went on to become NASA's chief scientist, pushing the agency's priorities towards Mars exploration that eventually led to the creation of the Mars Exploration Rovers, the Mars Reconnaissance Orbiter, and the Mars Science Laboratory. So why is a scientist clearly fixated on Mars intrigued by new land on Earth? The truth is, the two systems are actually cosmically related.
I think these small islands, small volcanic islands, freshly made, evolving rapidly, are windows into the role of surface waters on Mars as they have affected small landforms like volcanoes. And we see fields of them on Mars.
There's a lot to unpack there, but before you can understand the major significance of this on Mars, you have to understand why it's a big deal on Earth.
It really felt like we were, witnessing something that nobody else had seen.
That's the voice of Dr. Vicky Farini, one of the first pairs of eyes to see the new island from the deck of her research vessel.
It's this crazy, huge landmass that's sticking up out of the water where we know there wasn't one before.
We watched this island change, and it got more and more exciting. It didn't wash away. While there was massive erosion, there was redeposition, protecting the island.
So the initial mass above sea level was eroding very quickly over the first 3 to 6 months, and then it leveled off. So you kind of see a curve, a logarithmic fall off in change of that mass above sea level.
Basically, the island dramatically changed shape and size every day for the first few months. About 6 months in, it finally stabilized. Vicky's initial measurements and observations were crucial, but their research ship couldn't get close to the island without risking a collision. 2 French explorers who were sailing past the island on their worldwide voyage became NASA's eyes and ears, collecting some of the very first images and samples of the interior island.
This is the Earth at its best, because new land, new life, new landscapes, new patterns. How do they all work together?
The combined observations, satellite images, samples, and 3-dimensional topographical maps led Jim and the team to make some pretty stunning preliminary conclusions. Scientists think that, in this case, warmed seawater interacted with ash after the eruption, chemically altering the fragile rock into a tougher material. But studying the life and death of land on Earth also has much broader implications. This island may give us insights into if and how life formed on Mars in its early history.
Islands like this might have worked on Mars 2 or 3 billion years ago. Lakes and small seas, filling depressions, persistent surface waters. The stuff we really strive to understand because it could have produced the conditions necessary for microbial life, or not.
While the verdict is still out on whether or not liquid water on the surface of Mars may have produced life, scientists are currently running detailed chemical analysis of the island rock samples that will hopefully provide more answers in the months to come.
Earth is a magical place because really it's our point of departure for everything. And we've come to realize in the last 100 years or so that it's a far more dynamic world than we ever thought.
Which begs the question, what new secrets will this planet we think we understand so well reveal in the next 100 years?
I hope that you enjoyed that tie-in to sort of show you how something that seems so simple, a tiny volcanic island forming in the South Pacific, can get shot forward and inform us about how life could have potentially formed and then unformed on Mars, or if we're really lucky, potentially still exists below the surface. I want you to find as much job happiness as I have. And so think about all of these amazing careers that you could have that don't require you to sit behind a desk all the time.